Muy buenos días para todos y todas. Bienvenidos a los encuentros académicos del capítulo estudiantil del American Concrete Institute ACI de la Universidad Nacional de Colombia. Antes de comenzar, les voy a leer el orden del día de este webinar. Primero, daremos unas palabras de bienvenida en español y en inglés. Segundo, la presentación del ingeniero Bill Baker en español y en inglés. Tercero, la conferencia del ingeniero Bill Baker titulada Theory and the Design of Structures en inglés. Al final de esta conferencia se abre un espacio de preguntas y cierre en inglés. Posteriormente se realizará la presentación del profesor Juan Tamasco en español, su conferencia titulada Cómo hacer un diseño sismorresistente. Al final de la conferencia se abre un espacio de preguntas en español, se hace el cierre de la conferencia y al finalizar daremos unas palabras de cierre y finalización del evento en español. Entonces, empecemos. Permítanme presentarme, mi nombre es Edgar Nicolás Fuentes Alfonso, soy ingeniero agrícola e ingeniero civil de la Universidad Nacional de Colombia, sede Bogotá, y actualmente curso la maestría en Ingeniería Estructuras en la modalidad de investigación. Además, me desempeño como presidente del capítulo estudiantil del American Concrete Institute ACI en nuestra universidad. Cuando pienso en el diseño de estructuras, vienen a mi mente los nombres de dos ingenieros fundamentales en la historia de la ingeniería estructural, Fazlur Rahman Khan y Vitelmo Victorio Bertero, reconocidos como Hombre del Año por la revista Engineering News Record en 1972 y 1990 respectivamente. Fazlur Khan, pionero en el diseño de edificios de gran altura y principal responsable del John Hancock Center y la Torre Sears como socio de la firma Skidmore, Owings & Merrill, SOM, dejó profundas enseñanzas en el campo del diseño estructural, destacándose especialmente por la introducción del sistema tubular en rascacielos. Su mayor legado fue haber impulsado más que cualquier otro un verdadero renacimiento en la construcción de rascacielos durante la segunda mitad del siglo XX. Khan representó la máxima expresión de los logros en ingeniería estructural y al mismo tiempo subrayó la importancia de la colaboración creativa entre arquitectos e ingenieros. Para él, el diseño arquitectónico solo alcanzaba su máximo nivel cuando estaba sólidamente fundamentado en las realidades estructurales. Hoy tenemos el honor de contar con la presencia del ingeniero Bill Baker, uno de los profesionales que tuvo el privilegio de trabajar junto al ingeniero Khan en la firma Skidmore, Owings & Merrill. Si Khan revolucionó el mundo de los rascacielos, el profesor Vitelmo Bertero transformó para siempre el campo del diseño sismorresistente, reconocido por el Applied Technology Council, ATC, como el ingeniero sísmico más influyente del siglo XX, dejó un legado invaluable desde la Universidad de California en Berkeley, donde fue profesor y director del Centro de Investigación en Ingeniería Sísmica. Motivado por haber vivido un terremoto en Argentina, desarrolló el primer dispositivo capaz de ensayar muros de corte bajo cargas dinámicas. En la década de 1960, lideró una de las primeras pruebas de cargas sísmicas en estructuras de acero, hallazgos que fueron confirmados tras el terremoto de San Fernando, California, en 1971. Más adelante impulsó el reconocimiento del confinamiento del concreto, introdujo el factor de reducción de capacidad R en distintos sistemas estructurales, perfeccionó las pruebas en aisladores de base y defendió la necesidad de invertir más recursos en ingeniería sísmica. En síntesis, mientras Khan marcó la era de los grandes edificios, Bertero sentó las bases del diseño sismorresistente moderno. Dos ingenieros que con su visión y su trabajo cambiaron para siempre el rumbo de nuestra profesión. En Colombia, uno de los líderes más destacados en este campo es el profesor Juan Tamasco, motivo por el cual es un verdadero honor contar con su presencia en el día de hoy. Por todo lo anterior, es para mí un privilegio presentar hoy al ingeniero Bill Baker y al ingeniero Juan Tamasco, referentes internacionales y nacionales en la investigación y el diseño de estructuras. Agradecemos su participación, les animamos a hacer preguntas y compartir sus inquietudes al final de cada conferencia, que esta jornada sea un espacio de aprendizaje inspirador y enriquecedor para todos. A continuación presentamos ante ustedes la conferencia titulada Theory and the Design of Structures. Esta conferencia está a cargo del ingeniero Bill Baker. Bill Baker es uno de los ingenieros estructurales más destacados del mundo. Ha diseñado estructuras innovadoras que abarcan desde viviendas unifamiliares y pequeños puentes peatonales hasta el edificio más alto del mundo, el Burj Khalifa en Dubái, de 828 metros de altura. Entre sus diseños más vanguardistas se encuentran el singular Broadway Exchange House en Londres, que funciona a la vez como edificio y puente sobre la estación Liverpool Street, y el pabellón de acceso con cables tensados en la sede de General Motors en Detroit. Además, Bill Es ampliamente reconocido por sus colaboraciones con renombrados artistas como James Carpenter, Janet Shellman, Íñigo Manglano Ovalle, James Turrell y Jaume Plensa. Muchas de las innovaciones estructurales de Bill son fruto de su extensa investigación en sistemas estructurales, conocimiento que comparte a través de su enseñanza en conferencias y numerosas publicaciones. Es profesor honorario de la Universidad de Cambridge y también ha impartido clases en el MIT, la Universidad de Illinois en Urbana-Champaign, el Instituto de Tecnología de Illinois, la Universidad de Northwestern y la Universidad de Princeton. Bill ha recibido doctorados honoris causa de la Universidad de Stuttgart, la Universidad Heriot-Waite, el Instituto de Tecnología de Illinois y la Universidad de Missouri. Ha sido distinguido con la medalla de oro de la Institution of Structural Engineers, STE, el premio ASC Opel Lifetime Award for Design de la Sociedad Estadounidense de Ingenieros Civiles, la medalla de oro Gustav Magnell de la Universidad de Gant, la medalla Fazlur Rahman Khan del Consejo de Edificios Altos y Hábitat Urbano y el Fritz Leonard Prize. Bill posee un título de pregrado en Ingeniería Civil de la Universidad de Missouri, Columbia, y una maestría en Ingeniería Estructural en la Universidad de Illinois en Urbana-Champaign. Actualmente es socio consultor de la firma SOM. So, give me a second. Okay. So, bueno. Good morning, everyone, and welcome to the academic meetings of the ACE student chapter at the National University of Colombia. Allow me to introduce myself. My name is Edgar Nicolás Fuentes Alfonso. I am an agricultural and civil engineer from the National University of Colombia, Bogotá campus, and I am currently pursuing a master's degree in structural engineering with a research focus. I also serve as president of the student chapter of the American Concrete Institute, ACE, at the University Nacional of Colombia. When I think about the structural design, two names come to mind, two figures who shaped the history of the structural engineering, Fazlur Rahman Khan and Vitelmo Victorio Bertero, recognized as Man of the Year by Magazine Engineers News Record in 1972 and 1990, respectively. Fazlur Khan, a pioneer in tall building design and lead engineer of the John Hancock Center and the Sears Towers as a partner at SOM, left a profound mark on structural design, particularly with the introduction of the tubular system in skyscrapers. More than anyone else, he ushered in a true renaissance in high-rise construction during the second half of the 20th century. He embodied structural design achievement while highlighting the importance of creative collaboration between architects and engineers. For Khan, architectural design could only reach its highest potential when firmly grounded in structural realities today. We are honored to welcome engineer Bill Baker, one of the few who had the privilege of working alongside Khan in Skidmore, Owens and Merrill. If Khan revolution is skyscrapers, Professor Vitelmo Bertero forever transformed earthquake-resistant design. Recognized by the Applied Technology Council, ATC, as the most influential seismic engineer of the 20th century, he left an invaluable legacy from the University of California, Berkeley, where he was a professor and director of the Earthquake Engineering Research Center. Motivated by his own experience during an earthquake in Argentina, Bertero developed the first device capable of testing shear walls under dynamic loads. In the 1960s, he led one of the early seismic load tests on steel structures, findings later confirmed by the 1971 San Fernando earthquake in California. Later, he advanced the understanding of concrete confinement, pioneering in the use of the air capacity reduction factor in different structural systems, refined testing methods for base isolators, and championed the need for greater investment in earthquake engineering research. In short, while Khan marked the era of tall buildings, Bertero laid the foundation of the modern earthquake-resistant design. Two engineers whose vision and work permanently changed the course of our profession. In Colombia, one of the foremost leaders in the field is Professor Juan Tamasco, which makes it a time honor to have him with us today. For all these reasons, it is my privilege to introduce Engineer Bill Baker and Professor Juan Tamasco, international and national leaders in research and structural design. Thank you for all being here. We encourage you to ask questions and share your thoughts at the end of each presentation. May this event be an inspiring and enriched learning experience for everyone. So next, we are pleased to present the lecture titled Theory and the Design of Structures. This lecture will be delivered by engineer Bill Baker. Bill Baker is one of the world's leading structural engineers. He has designed innovative structures that range in scale from single-family homes and small pedestrian bridge to the world's tallest man-made structure, the Burj Khalifa in Dubai. His cutting-edge design include the unique Broadway Exchange House in London, which is both a building and bridge that spans over Liverpool Street Station, and the cable support entry pavilion for the General Motors headquarters in Detroit. Additionally, Bill is widely recognized for his collaboration with renowned artists such as James Carpenter, James Enchelman, Inigo Manglano Valle, James Turrell, and James Plensa. Many of Bill's structural innovations are a result of his extensive research in structural systems, which he shares through his teaching lectures and numerous publications. He is an honorary professor at the University of Cambridge and has also at MIT, the University of Illinois at Urbana-Champaign, Illinois Institute of Technology, Northwestern University, and Princeton University. Bill has received honorary doctorates from the University of Stuttgart, Heriot-Watt University, the Illinois Institute of Technology, and the University of Missouri. He has been honored with the gold medal from the Institution of Structural Engineers, TA, the American Society of Civil Engineers, ASSE Opel Lifetime Award for Design, the Gustav Magnell Gold Medal from the University of Ghent, the Fazlur Rahman Khan Medal from the Council of Tall Buildings and Urban Habitat, and the Fritz Leonard Prize. He holds a bachelor's degree in civil engineers from the University of Missouri, Columbia, and a master's degree in structural engineer from the University of Illinois at Urbana-Champaign. He is Skidmore, Owings & Merrill consulting partner. It is my pleasure to introduce Mr. Bill Baker.
Okay, well, thank you very much for that introduction. And what I'm going to talk about today is, I think, a very important topic, which is the creation of structures, and particularly the use of theory in the creation of structures. And so and the reason we're doing this is because we have this challenge. The challenge is to create ideas and technologies that will lead to efficient structures. And I find that the most fruitful place to look on this is a focus on the geometry of structure. And let me explain a little bit why geometry matters. Structural systems are, of course, essential for efficiency, but geometry is critical to structural systems. Here I showed two different trusses that do exactly the same job. There are 3-to-1 cantilevers, truss A and truss B. But if you're controlled by strength, the one on the left needs 27% more material than the one on the right. And if you're controlled by deflection, the one on the left needs 60% more material than the one on the right. And the difference between the two of these trusses is fundamentally geometry. And the efficiency of structures is very important, particularly in these days of concern about the climate, because on day one, most of the carbon of a new building is in the structure. And geometry is also the intersection of architecture and structure. It is the common language to the both disciplines. And we'd like to introduce a little terminology to you that's helpful in this discussion. I want to talk about topology, shape, and size. We'll start with here the geometry terminology for design. We have what we call the design domain where the structure might exist. And there's three geometrical aspects of this. Topology, which is what is connected to what. Shape, which is how do you take that topology and move the nodes around, if you will, to create an efficient shape. And then finally, how do you size the members? Now, topology and shape are very highly related to architecture and the form of the building, but these are extremely important in the design of efficient structures. So it's important that the structural engineer is involved in determining the topology and the shape of the structure. So how can one create efficient structural systems? I think you have to look to theory for design ideas. And so today I'm going to present a few of my favorite theories, if you like, that are very helpful. I'm going to start with something called the Maxwell load path theorem that was created by Maxwell in 1870. James Clerk Maxwell, I'm going to refer to many times today. He is, of course, very famous for his work in electromagnetic theory, but he's also did some very important work in our world of structural engineering. He wrote this paper in 1870 it's called On Reciprocal Figures, Frames, and Diagrams of Forces, where he describes some very important ideas, including this particular theory. So I'm going to start out with a proof of the Maxwell a proof of the load path theorem for an externally loaded truss. Here I have a truss. It's in equilibrium. I have a series of external loads, and I have a series of internal forces. So the red arrows here represent compression forces, the green arrows, tensile forces. And what I'm going to do, I'm going to keep the forces, and I'm going to throw away the members, but I'm going to keep the forces. And every node, it's important to recognize that every node is in equilibrium. All the forces add to zero at each node. And now what I'm going to do, I'm going to take these forces, I'm going to dilate the space. I'm going to pick an arbitrary origin, say like right here, it could be anywhere. And I'm going to dilate the space. I'm going to make all the vectors twice as far from this origin. And as I do that, I do a series of work. First of all these dimensions have just gotten twice as long. All the lengths are twice as long. All the external forces are twice as far from the origin as they used to be. And so we've done a series of works. The external forces have done external work. The internal forces, the compressive members have grown by twice the length. So it's the force times the length is the work done. If I look at the tensile members, they're also twice as long. And they've done negative work because their arrows are opposite in the opposite direction of the elongation. And therefore, they've created negative work. But because every node was in equilibrium, all of these forces have to add to zero. Because in essence, we've done no work because all the nodes are in equilibrium. And so what we could do is we can take this and rearrange it. And this is the Maxwell load path theorem, where the force in all the tension members times their length minus the force in all the compression members times their length is equal to this dot product of the external forces dotted to a position vector from any arbitrary origin. Now, for many, many structures I deal with, and you will deal with in your career, this is a constant. And so what it tells you that in many cases, the tension load path minus the compression load path is a constant. And we call this dot product to the right, we call that the Maxwell number. And so let me give you an example that was related to that picture I showed you earlier. So we're going to do a Maxwell load path theorem, a cantilever example. Here I have a cantilever. I've got a load out here, and I've got some supports back here. So it's a 3-to-1 cantilever. And the moments are taken out by this couple, this 3P and this 3P. And I have the vertical loads are handled here. And I'm going to apply Maxwell load path theorem to this. I'm going to put the origin right here because I can put it anywhere. This happens to be a convenient place. And now I'm going to do a dot product from this origin to all the perimeter loads. Because the dot product to this load is 0 because these are orthogonal to each other. Here at the origin, the length is 0, so this dot product is 0. I'm going to do a dot product to this horizontal reaction. It's because they're orthogonal to each other. This dot product is 0. And then finally, I'm going to do a dot product to this load at the top, and I get a value of PB. Now, so that tells me the sum of all my dot product for all my external forces is equal to PV. Now, take just a moment to reflect on it. I have not even proposed a structure, but I already know the difference between my tension load path, the force in all the tension members times their length, minus the compression load path. And I don't even know what the structure is. So let's try a structure. Let's try the moment diagram. Here I have a compression member, which has a force of 3P, and it's a length of 3B. So my compression load path is 9PB. My tension load path, I have a tensile force of the square root of 10 times P. My length is the square root of 10 times B. I multiply those together and I get my tension load path is 10 PB. My difference is exactly what Maxwell told us is equal to PB. Now, if I look at my total load path, I'm going to add these two numbers together and I get 19 PB. But I'm also going to look at how much it deflects. I'm going to use virtual work, and my deflection here is 19 stress times B over E. And I'm going to look at my volume, which is my load path, assuming I have a constant stress in all of my numbers. My load path, my force times my length divided by the stress. And it's important to note for this particular case, this is not true in all cases, that these have the same correspondence. But can I be more efficient? Because the difference is going to be the same, I don't have to try to minimize both of these. If I minimize either the compression by itself or the tension by itself, I will automatically optimize the other. So let's try a Pratt truss, okay? And now if you go through the math, you're going to see that my compression load path has now gone from 9, this was 9, now it's down to 8. So I have 1 PB plus 2 PB plus 3, that gives me 6, plus these verticals, 7, 8. And I look at my tension load path, it turns out to be 9. My difference has not changed. A completely different structure, but my tension load path minus compression load path has not changed. My total load path has gone down. I actually have smaller deflection and less material. Let's try another solution. Let's try the Warren truss. Okay, so here I go up and down and up. Now my compression members is 3 times B and P times 2. That gives me 5 plus my diagonal gives me 7. So now I'm down to 7. My tension members are 2 times 2. This is 4 plus another 2 is 6 plus another 2 is 8. But my difference has not changed. My total is now down to 15. My deflection is even less, and my volume is less. And the remarkable thing about this is the structure with the least material has the least deflection because we're changing the geometry. Now, a reasonable question is, how low can we go? Can we find a benchmark for our design? What's the lowest we can go? Well, now we're going to go to theories by Mitchell, okay? And this is called a discrete Mitchell truss. Mitchell derived his theory based on Maxwell's load path theorem. And here it's an odd-looking structure. It's got certain geometric properties. But here my compression load path is this number, and there's my tension. The difference is the same. And now I'm down to 13.9. So, but if I could go even lower, I could if I do an even more complex Mitchell truss. I get down to here, but this is as low as I can go, around 13.17. I can also come up with different structures, which are interesting. Let's say I only want one compression member. This is a discrete Mitchell truss that only has one compression member. And it turns out that all of these angles from the tension members to the compression members are identical. And this comes from theory. It's not something I created. It comes from the Mitchell theory. And now this is a 16. It's not as efficient because I've constrained the problem, but I think it's a very elegant geometry. So let's compare our lowest value, which is pretty odd-looking structure, with a more conventional, more easily built Warren truss, and I can see how close I am. I'm within 14% of the lowest possible value. Now, and this coefficient is very important. Here I can compare this moment diagram truss with the Warren truss. And here my deflection is 19 times stress over BE. And this has 15 times the stress in this structure. And so I'm going to take this deflection. I'm going to calculate for a given deflection. I get a stress. I put that here. My volume from the earlier slide is this much. And so if I do my volume in terms of my deflection, I get this 19 squared PB squared over my deflection for the stress times E. And if I do the same thing for the Warren, I get this coefficient over here of 15 squared. And so if my deflection of these two trusses is identical, if delta 1 equals delta 2, my volume for the one on the left has to be 60% more, hugely inefficient compared to the Warren Truss. And this is very important for the design of a structure like this. If you want to optimize this particular structure, this is an exchange house in London. It's a building that's also a bridge. You can optimize it by just minimizing the tension load path only. And you do not ever have to calculate the forces in the arch in order to determine the minimum or the most efficient height of truss. You just have to minimize your tension load path. You can even use this approach to estimate the entire structure by only calculating the Maxwell number, which is the weight of the building times half the height, and the tension members, and you can come up with an estimate of the total structural material for the entire structure without ever calculating any of the compression numbers. Let me go to another theory that Maxwell did, which is we're going to get into the geometry of 2D equilibrium using a process called graphic statics. It's also often called the Cremona method. This was developed by Maxwell, but he developed this in 1864 in this paper, which has almost the same name as the paper I showed you earlier, slightly different. This is called Reciprocal Figures and Diagrams of Forces. And he talks about this paragraph, which is hard for us to understand in the 21st century, but it would have been well known in the 19th century, which is reciprocal figures are such that the properties of the first relative to the second are the same as the second relative to the first. And so here we have two diagrams. One on the left is we're going to call the form diagram. It's obviously a truss. And the one on the right, we're called a force diagram. And these is a graphical representation of the forces. And every bar over here has a label where you, like this is between different polygons. This is between two of the external forces is considered an open polygon. And so this member has the name of B6. If I want to know the force in member B6, I go over here and I look at the length from little b, B3, the force in member B3. I go from B down to node 3. So the length of this line is a measure of the force in this member. And how was this done? It was done very simply. You would go around your structure first on the outside, and you take all your external loads and you line them up. So this is the load from A to B and then B to C. And you line them up here, A to B, B to C, C to D, D to E, E to F. Then you get your reactions from F to G, takes you up to here, and your other reaction from G to A to back to where you started. And these are your external loads. And then just using straight lines, you would pull these lines over and you would automatically, graphically calculate your forces. And so the length of these two lines are the forces in these two members. And this line is parallel to this line, and this force is parallel to this line. So you just keep going. And through this very, very simple graphical method, you can calculate all the forces in all the bars. And this is how our predecessors used to calculate structures. And in the end, you'd have these two diagrams. One represents the geometry of the structure, the other, the geometry of the forces. So, but we have other tools for doing analysis today, but I find graphic statics very, very powerful for design. So with graphic statics as a design tool. So let's instead of designing the structure, let's design the forces. And so what if we don't like these forces? What if we want this rafter, this cord here on the top, we decided we're going to use one member for all of this. So we want the forces in each of these to be identical. So how could you do that? Well, draw the forces. So here, I've drawn the forces where they're all exactly the same forces. And now I have to use graphic statics to figure out the rest of the geometry. And I do that by using the rules of graphic statics. And in the end, I've now had this structure where it's totally in equilibrium. The forces in my top chord are all equal. And what's interesting, you'll see each of these nodes maps to each of these polygons maps to a node over here. And let's look at 3 and 4. It turns out like, that they, sorry, let's look at 2 to 3, okay? And you'll notice that 2 to 3 are at a point. So there's a line there, but it has no length. So therefore, this member has 0 force. And so there you have a funicular shape. It looks a little odd, but one of the greatest engineers of all time used that to design a warehouse that's over 100 years ago in Italy. Robert Maillard did this. And you have to remember that one of he designed some of the most beautiful structures in the world, and he did them all with graphic statics. Here's one of his most famous bridges, and here are his calculations, his graphical calculations for that bridge. And you can imagine if you're designing graphically at the same time you're drawing the structure, there's got to be this incredible feedback loop. You can do it other things. Here, let's say you want a truss where the force and all the top chord members and all the bottom chord members are identical. You can easily do that with graphic statics just by drawing the forces. And then you figure out how it comes together. Now Maxwell did something else, which is an extension of graphic statics. So once again, we're going to go back to his paper from 1864. And he had this concept. In order to do graphic statics that I just showed you, he made this amazing observation that hence the condition of the possibility of a reciprocity in plane figures are the same as those of each figure being the perspective projection of a plane-sided polyhedron. What does that mean? Well, here we have a truss, okay? Here we have a truss. It's in equilibrium. The black lines are the force members. The red lines are the external forces. From graphic statics, we know the force in all the members. Let's say I wanted the force in member, say C4. Well, it's the length from C to 4. That's the force in this member. It's all there. Well, I'm going to use a little technique that was given to us by Rankine. I'm going to put a little dot over here. And that dot is going to go to all these loads on the external forces. And what I've created is essentially a funicular structure, where if I took these red forces and I put them on this as for a string, it would all be in equilibrium. And so now I'm going to take this up there. And now my truss is, these marine members all have forces. And if I know the force in one of these red members, I know the force in all of them. And it's loading this black truss. So the forces in the black truss have not changed at all, but I've made what I'm calling a self-stress structure. It's a structure that it pushes on itself. And what Maxwell observed is because that's an equilibrium, it's a projection of a polyhedron where every face is exactly flat. And furthermore, the force in each of the bars is proportional to the change in slope between all the faces. Totally remarkable. That equilibrium in the 2 dimension is related to a plane face polyhedron in the 3rd dimension. And here I've separated the forces in the truss from the forces in the loading system. But the change in slope is proportional to the force. All the ridges are compression members. All the valleys are tension members. And it turns out that this polyhedron has a reciprocal polyhedron, which maps to the forces. So it's incredibly rich 2-dimensional, 3-dimensional geometry between form and forces. What is that polyhedron? Well, it turns out that polyhedron goes from another theory, the Airy stress function. George Bedell Airy created the stress function. He was curious about, in fact, he said this in his paper, he was fascinated by Robert Stephenson's Britannica Bridge, this early box girder, and trying to figure out the forces in those boxes. And so the Airy stress function, where you take equilibrium on an infinitesimal piece of material with some body forces. From mechanics, we all know how to do this. Here's your equilibrium in the x direction, your equilibrium in the y direction. In this case, we're going to throw away the body forces. And now we're going to assume that there exists a function. We're going to call this the Airy stress function, phi, where the second derivative of phi in the y direction is stresses in the x direction. Just accept this, okay? Say this is an assumption that you're going to make, and that the second derivative in the x direction are the stresses in the y direction, and the second derivative across the negative of the cross derivative is the shear stresses. If you make those assumptions and you use your equations of equilibrium, you will find that you will always satisfy equilibrium with the Airy stress function. Always. Okay? Now, the trick is you got to come up with an Airy stress function that matches the boundary conditions. Not always so easy, but here, so let's say your Airy stress function is a series of slopes, like that truss I just showed you. Well, it turns out that the change in slopes from one face to the other is proportional to the forces. And just as I told you, all the ridges turn out to be compression forces, all the valleys are tensile forces, and because I'm going from a flat surface to a flat surface, I am in equilibrium. These forces exactly add to zero. Now, how can we use this? Well, let's use that to design some grid shells, all right? But now I want to point out some very important things. Three-dimensional structures are very difficult, right? But for a three-dimensional structure to be in equilibrium, the two-dimensional projection has to be. Now, here's a model I made in my office. Clearly, it's loaded by gravity. It's a chain model, it looks all curvy. But if I look straight down on it, I'm looking at a two-dimensional projection of three-dimensional equilibrium, and I no longer see gravity. Think for a minute. I'm looking parallel to gravity, so I no longer see gravity. All I see are the horizontal forces and the reactions at these posts. And as I just told you, because this is a two-dimensional structure in equilibrium, I'm also looking down at an Airy stress function, a polyhedra that has exactly flat faces. But I could take this two-dimensional structure, I can replace these red reactions with a reaction frame, and now I have a self-stress structure that is in equilibrium. It's in two-dimensional equilibrium, but we know it can also be the projection of a structure that is in three dimensions. And so what I find very easy in design is to do my designs in two dimensions using equilibrium and then projecting to the third dimension. And to do this, I'm going to go to the theory. I'm going to go into Timoshenko's a book, and we're going to look at a theory by Pucher. So we're going to go to Timoshenko's book on the theory of plates and shells. And if you go in there, he presents a theory by Pucher. And this is on the membrane of a shell, but it's a shell that all the forces are up here in the membrane. But we're going to project, just as I was saying, we're going to take this load that's in three dimensions, and we're going to do all our mathematics about the XY projection of this. So all of these forces that are in the membrane, we're going to project down into the horizontal plane, and then we're going to calculate our equilibrium. And after a bunch of basically just algebra, it's really quite straightforward, you'll end up with this equation where to design this grid shell, you have the Airy stress function and the geometry of the roof. Those are the only two things you have. You've got this, and you'll see that the Airy stress function, the second derivative of the y direction, times the shape of the roof, which is the second derivative of the roof, the z coordinates, in the x direction. So they're orthogonal to each other. And you'll see that the Airy stress function and the roof are equally important. And in this equation, this F is the uniform downward load on this membrane. Now, this is calculated about the projected area, but this is the vertical load, and this will give you equilibrium for a membrane structure. And it's very, very important to note that you actually have two geometries now. You have the Airy stress function and the roof, and both of them will satisfy equilibrium. So let's design a grid shell using the Airy stress function. So here is the plan dimension. I've done a triangulated grid, and this is important so it can develop horizontal thrust. If I'm going to do something, if I'm designing a three-dimensional structure that has force, I have to have a two-dimensional structure that can thrust. Okay, this can clearly thrust. And so notice I've triangulated and it can thrust into the corners. And so now I'm going to guess a shape. Here, I'm going to guess a shape of the roof. And this is my Airy stress function. I'm not very happy. It's a pretty ugly Airy stress function. And this is a representation of my forces. I got some hot spots in the corners. And I can tell from the Airy stress function that maybe this is not a good guess. So let me try another guess. Okay. And so let me play around with the corner geometry of this guy and see if I can make it a little better. By the way, either one of these could be the roof. This is the roof, and this is the Airy stress function. If this is the roof, it doesn't drain very well. It's pretty ugly, but this would be the Airy stress function. Okay, so let's try something else. Let's modify this shape a little bit. Maybe a little bit better, but not a lot better. Once again, either one of these could be the roof, and the other is the Airy stress function. But you can clearly see because I had some really big changes in slopes, I got some really big forces in some of these members. You can see that here in this diagram. So what am I going to do? Well, let's go to electromagnetic theory. And let's use the Biot-Savart law, and we'll put an electrical current in this wire forming a polyhedron, and we'll look at the magnetic field using the Biot-Savart law, and we'll use that to create the shape. Oh, now things are looking pretty good. Here I have two shapes. If this is your roof, this is the Airy stress function. And you can see if I look at the Airy stress function, it's pretty smooth. I do have this change in slope right here, which represents this force, this thrust here. And what you can see is like the perimeter is acting like a restraining truss. So the roof is trying to thrust against the edges. And in the process, it's doing. Now, what's also very interesting, that if this were my roof, you can see that this would be my Airy stress function, and I have very, very smooth forces. The change in slope from one face to the next is very smooth. So if this were my roof, it's maybe not as attractive as the one down below, but it does have very smooth forces. But either of these would be acceptable as the roof, in my opinion. Okay. Now, and I think it represents a good engineering solutions with very little tension and uniform forces. In fact, most of the tension is in this perimeter, which acts like a tension ring around this field of compression. And you can see most of these members have very, very small forces. And remember, either one, the roof or the Airy stress function can be swapped. You actually have created two solutions to your problem. Okay, now I'm going to go to one of my other favorite theorems. This is virtual work. Once again, we have to go back to Maxwell. This one's another paper, a different paper from 1864. This is called On the Calculation of Equilibrium and Stiffness of Frames. And so I'm going to do it using a little bit different technique than Maxwell did. So let's say I have a structure that has some loads on it, and I put the loads on uniformly from 0 to thing. And so as I put the loads on, the building starts to deflect. And I got these deflections cause external work, but I also develop elongations of all my members. either tensions or compressions, either compressive compression or elongation. And all of them have forces. So I'm doing my external work. That's because I brought the load on slowly. Now my external work is 1/2 times my final forces times the change, the displacements, all the nodes. Now this is the displacement in the direction of the load, okay? Because this is the external work done. And that is equal to the internal work, do conservation of energy. So that's equals the force in all the members times the change in length of all the members times the half. And you add all these up and they have to be equal. Now let me do a little bit of a different problem. Let's say I have a structure and it's already existing there. It has a load on it up here, capital V, and all the bars have a load in it, and it's in equilibrium. Now I'm going to take this structure that's already has this load in it, and I'm going to add loads like I did in the previous slides. I'm going to add these loads, and I'm going to put them on slowly. And in the process, I'm going to get, as I put these loads on P1, 2, 3, and 4, I'm going to get deflections at each of these nodes where the loads are applied. I'm going to get forces in all the members due to these new loads. I'm going to get an elongation of all these members or shrinkage of all these members due to these new loads. And this node here, the one that this load V on, is going to move. And I'm going to call that delta star. Okay, and so we put all these together, and now we have one structure. Now let's calculate our external work and our internal work. Where our external work, now this load that was already on there has moved over by delta star, so it's on the work of V times P star. There is no 1/2 here. Okay, but these loads that came in the second load case, they will have the 1/2, just like we had on the previous slide, the force times displacement times 1/2. Now this external work has to equal the internal work. Well, what is the internal work? Well, it's the force in these bars that was already there times the change in length of the bars. Add those up. No 1/2 on this one, and then the elongation due to the new forces and the loads. But we know that these blue loads here are equal from the previous stuff, so I can throw them away, and I'm left with this this force here, where you have the load from the first case times the displacement from the second load case, times the summation of all the forces in the bars from the first load case, times the change in length from the second load case. Think about that for a minute. This is totally bizarre. Totally bizarre. You've got forces from one load case times the displacements from a second load case. But this is brilliant because it tells you amazing things. So what if I really want to know about, if I'm really, a critical design criteria is how much does this structure move in this direction at that point? And so this has amazing properties. Now I'm going to divide both sides so that my virtual external work is equal to my virtual internal work. I'm going to divide both sides by V. So now this is called a unit load. So V, little v's by capital V. And so my displacement is equal to the summation of the unit loads from my force and all my members from the unit load case times the change in length from the second load case. Here I have change in length. Now this change in length, let's save, so I got my element forces due to the virtual unit load and the elongations due to the real loads. And so it's the displacements due to the real loads in the direction and the location of the virtual load. Now that change in length is, the change in length is strain times the bar length, which is stress over modulus times the length, which is, as we're used to saying, force times length over EA. The stiffness of this bar is EA over L. So the change in length is this F over L. So this is how I normally write it. my virtual work is the change in length equals the summation of the unit loads times the force in the bars times the length divided by EA. Now, the bars don't actually have to be straight. They can be curved. You just have to have a linear relationship between the force and the displacements. Now, this is incredibly useful in design, one of my favorite tools. So it's great for solving geometries. Okay, so this tells you how I put a unit load here. I'm concerned about the top, how much my building moves to the top. This tells me how important every member is. This guy is only important of 1. This guy has an importance of 4. What does that mean? What if, for instance, so we have virtual work 4. What if this bar here was shipped to you the wrong length? So let's say it's precast concrete, and they ship it to you. They made a mistake in the factory, and it's short by a dimension delta. And you want to know how much what is that going to do to my structure? You could do a really complicated geometry thing. No, you use virtual work. I know that this will move 4 delta from virtual work. Very, very important. So virtual work is a geometry solver. You can also use it for optimization. I'm going to use the theory of Lagrange multiplier. So here I have a structure. It's got real loads on it. I'm going to put a unit load on it, and I'm concerned about how much it moves at the top. So I put a single unit load here at the top, so I can figure out how to move. I'm going to use this thing. This is a very important equation. This tells you how much every single bar, every individual bar, what is its contribution to that deflection at the top. So FLEA. And not only to the deflection at the top, but in a particular direction. The virtual work, okay? Now I'm going to do some optimization using the Lagrange multiplier technique. So what I'm going to do is I'm going to take this thing and I'm going to add to it essentially 0. I'm going to make it a constrained problem. Here is the area of my bars times the length, which is the volume of each individual bar. I'm going to add them up, and that's going to be equal to my total volume. And so this is essentially 0. I'm going to multiply it times this constant called lambda. And it turns out, if you have certain constraints, that lambda is the same for every member in your structure. It's a constant for the entire structure. And so this is the virtual work. Here I'm assuming straight prismatic members. This is a non-zero Lagrange multiplier. This is the volume of each of the members. And so this green thing adds to 0. So I not really changed the problem. I just constrained it. So now I want to do a little optimization. So what I'm going to do, I'm going to do a little calculus. I'm going to take I'm going to do my first derivative. So if I have a statically determinate problem, I can do this. I'm going to take my first derivative of this with respect to my areas. Because my design variables are the cross-sectional areas of each of the bars. I can change each of the bar areas individually. So those are my design variables. So I'm going to minimize this with respect to area I. I do my first derivatives. And so because this is the denominator, I end up with the minus sign and a squared. You know this from calculus. And then I have my rate of change of member J with respect to member I. And then over here on my volume side, I have the same thing. Now my volume is constant, so this derivative is 0. And here, I take my derivative here, I end up with the same term. And because these are independent variables, I can change any area independent of any other. So this value is like the Kronecker delta. It's either 0 or 1. And so what that does, it blows apart your summation. So I no longer have to do the summation. I just look at each individual bar. And so I have this calculation. And it was interesting that my lengths cancel. And so for an optimal structure, my lambda is equal to force in each of the bars times the unit load in each of the bar divided by E divided by the area squared. And this term needs to be the same for every member of the structure, which is essentially saying that the virtual force and the real forces times each other divided by the modulus is a constant. Now, if you know this information, you can go through some algebra. I'll give you a reference to a paper, so we don't want to go into much detail. But once you know that, you can do some algebra. Now, this will work if the virtual work and constraining function are smooth, and the constraining function has a non-zero gradient, then lambda exists and is unique. And those are the kind of rules. And this generally applies to statically determined structure. I use this all the time, even on indeterminate structures, because it gives me a good idea of what I need to do. Okay, and this is in a paper. I'll give you a reference to in a minute. You get your, so once you do that, you say you have a target deflection you're trying to hit. So you take that value, and then from there, you can now use your target deflection, you can put in your optimal area. From that, you can now calculate what your lambda is. Once you know your lambda and your optimal area, you can put them together in the same equation, and you can simplify it to put those together. And now you can figure out the area of every member of your structure, which will be a minimum deflection in that direction at your point. A more intuitive approach is so here is the Lagrange multiplier. And this tells you, this is very, very important, that each member contributes this very calculatable member to the total deflection at the point. But each member also contributes to the volume, so the cost of the structure. How much embodied carbon is related to this. And so let's take the contribution to work, divide it by the constant. So when I figured this out, I was working on a very tall building. Fazler Khan was still around. I was working on one of Khan's projects. And I said, well, what if I divide the work by the volume? Seems like a good idea. Guess what? That's what the Lagrange multiplier. It's the virtual work divided by the volume. So what you end up with is that you have a uniform virtual work density. So lambda is virtual work density and is uniform at optimal. Now, I'll move on to another theory, the theory of tall buildings. We have, a tall building is just a giant beam. Here I show you the Sears Tower. Now we call it the Willis Tower. It was the world's tallest building for many, many years. I think 25 years or so, 30 years. It was the world's tallest building. If you got to think of that as one single beam. If you think of it as thousands of beams and columns of what it's made of, that is too complicated. Our minds cannot deal with that. So continue it with a simple beam. And cantilever, it's a cantilever beam. Cantilever's out of the ground. And the theory of cantilevers goes back to Galileo. As you hopefully know, Galileo was the first modern structural theorist, and he wrote this treatise on the strength of a cantilever. He actually got it wrong, but he had some part of it right. But he started the conversation, and he did come up with some very correct interpretations, even if some of his mathematics weren't quite right. And so here he has this cantilever coming out of this ruin of a brick wall with a weight on it. Cantilevers like this, but a building is also a cantilever. You put a force on it and it deflects. And so a lot of times, here you have this tall building, which is a frame. You can think of it as a beam, okay? And for designing beam, we have flanges that take the moment. We have webs that take the shear. The web has to be connected to the flanges to make them work, because the overturning moment is the integral to shear. So shear and the stuff that resists the shear and the stuff that resists the moment have to be interconnected. And so in a building, you could, for many buildings, you could assume that say these columns act like the flange, and these columns and beams act like the web, the connected, and that's a pretty reasonable assumption. And we pulled this out of the archive here in the office because my firm also, did Sears Tower. But that here's an elevation of the building, and it goes from this. It's called a bundle tube. It's got this 3x3 matrix of these 9 bundles, and as you go from bottom to top, first 2 of them drop off, then 2 more, then 3 drop off. This is what you have at the top. And here is a simple calculation of the moment inertia. This is the moment inertia I, which is the area of all the bars, summation of the times the radius gyration of the columns from the neutral axis. And furthermore, it's a step function, but they took an equivalent approximation as just a straight line. And here are the forces at the bottom of the Willis Tower. They call it a bundle tube. To me, it's really more like it's like one giant beam with four webs. Okay, so here's a flange, here's a flange, here's kind of an intermediate flange, here intermediate flange, and it has these four webs that deliver the loads to the flanges. And here's the stress distribution at the bottom of the Willis Tower. As you can see, it's not exactly plane sections remaining plane, but it's pretty close. That is how we designed the Burj Khalifa. It's a giant beam. It just happens to be 828 meter tall beam. This particular beam is predominantly concrete. The very top is a spire. It's on a 3.7 meter mat. And here are the components. It's a bunch of walls that do the combined function of both delivering shear and being the flanges. So this is like a flange. This is like a web. And we gave it a name. We called it the buttress core. And if you look down, it's a giant structural shape of a beam. Now, in a tall building, you're very concerned about twist. You don't want it to torque. So we created this core that goes around the center, elevators and stairs. And it's like a tube, okay? It is a tube. And so it has very high torsional stiffness, so the building doesn't twist. But it's very slender to go 828 meters, too slender. So what we did is we buttressed it. This is a residential building, and so for privacy reasons, these wings, we used 120 degrees separation. So down each of the corridors, we have these webs going on. And then between the apartments, we have these walls, which act like flanges. So these legs act like webs and flanges. And then we also have some structure that reaches out there to grab these perimeter columns, like we call them nose columns. And that is how it is. When we designed this building, we actually calculated the radius gyration of the entire building. That's it. And this happens to be a very, very, very efficient beam with very little shear deformations. It's almost like a pure beam where plane sections are pretty much the remaining plane. And so, that was the final idea from this. As I told you, I'll give you a few references for the stuff on graphic statics and those techniques. I urge you to look at this article. There's also other articles like this is the American Institute of Steel Construction, the Engineering Journal from the third quarter of 2015. It's structural innovations combining classic theories with new technology. And then for the Lagrange multiplier and optimization, here's a paper I did many years ago called Energy-Based Design of Lateral Systems. I published this back in February 1992, a little while ago. This is in the International Association of Bridge and Structural Engineers, their Structural Engineering International publication. Okay, and so that I want to thank you for your attention. And now I've stayed on schedule. Okay, I'm running maybe 4 minutes over, and so with that, I guess we'll take some questions.
Okay, thank you, Mr. Baker. This was a great opportunity, and your lecture was truly remarkable. You took us from graphic statics as the way of the Burj Khalifa. So, thank you.
Yeah, it's about 150 years worth of engineering there. Okay.
Yes. Now, we open a space to question and answers. So I'm going to animate the chat to write your questions. So, Mr. Baker, I prepare one question for you.
Okay.
The first is, mm, regarding the use of the new tools, how do you perceive that advanced software and artificial intelligence are transforming the design process and the decision making in engineering?
Oh, okay, it's a very important question. Artificial intelligence can generally only interpolate. Artificial intelligence is best based on what's already been done. And if you as an engineer is going to do something that's never been done before, artificial intelligence may not get you there. Okay. And so, that's an important point. Now, the other thing is, but I'm sure, but we will all be using artificial intelligence, and it will give you maybe a result. But and a lot of times the results may be graphic, but you as an engineer need to have a very, very deep understanding of theory, because when the computer gives you a solution, if you have a deep understanding of theory, you will understand why the computer gave you that solution. And once you understand that, you can then change the problem and come up with a different solution. There's something called the Bader-Meinhof syndrome, which is there's a journalist, prisoner of Bader-Meinhof. They were a German terrorist group in the 1970s, and there was a journalist who had never heard of them, and then became aware of them, and had never noticed their names anywhere. They became aware of this group, and all of a sudden they saw their names everywhere. Well, it was always everywhere, but they weren't synthesized to see it. And so the importance of your deep theoretical knowledge is that you will look, if you and some other people are looking at the same results, you will see things that they do not see, because you have been made sensitive to certain information that you as an engineer will understand that they will not. And I truly believe, if you want to be a designer, and you want to be a designer who's going to do things that have never been done before, you need to study as much theory as you can. There's a very important firm here in the United States called Thornton Tomasetti. It was founded by a guy named Charlie Thornton. And I remember Charlie, we were talking one time, and Charlie said, continuum mechanics made his career. And you got to remember, one of my predecessors, Fazlur Khan, had 2 masters and a PhD.
Yes, in mechanics, theory, and structural engineering.
Yeah, one of his masters was in structural engineering. The other master was in theoretical and applied mechanics.
Yes.
And so, if you're going to do something that hasn't been done before, you better understand your theory.
Okay, thank you, Mr. Baker. Now I have a question from Diego Ordóñez. He said, Professor, who has an opinion on the philosophy of the design by performance?
Okay, yeah, I think, yeah, very much so. I think I don't have it here. When I was a junior engineer,
yes,
the rule book for loads was probably about this thick. Okay. And now this is it. Okay. 2 volumes. This is ACI. No, here. Yeah, sorry. Let me get it right. Okay. Here's ACI, and here's ASCE 7. Okay. Yes. Ridiculous. Okay. Too many rules. Okay. I think the chance of an engineer making mistakes because there's too many rules is much higher than having a problem from other reasons. And so I think moving to performance, which is rather than give a bunch of rules, give a performance. What is it you're trying to achieve? What is the behavior? What's the level of reliability or safety that you're trying to achieve? I think that's a much better approach. And the more rules the more you try to make our business into a cookbook, well, the cookbook gets really thick. Okay, and starts in many ways can can limit creativity. The very, very famous structural engineer Felix Candela.
Yes.
Okay, he was on the ACI committee for design of shells. Okay, and he resigned from the committee because he thought the committee was trying to write rules that was going to limit creativity in shells. And he wrote a very important letter. It's when I teach, sometimes I have my students read Candela's letter. Felix Candela's letter on his resignation from the ACI committee.
Okay, thank you, Mr. Baker. Continue. I have a question about by Jorge Alexander Niño. He said, what do you think about the viviendas? Is it efficient or not?
The vivienda truss is very useful. Okay, is it as efficient as a diagonalization? No, but sometimes you can't have diagonals. Okay, a lot of times we'll use these moment frames we do in tall buildings or these frame tubes are essentially Virendale trusses, but because diagonals have issues. If you have an office building, maybe you can have a diagonal and it's okay. If you have a hotel room, you can't put a diagonal, because all of a sudden no one will want that room. Okay, so there's that. So I find Virendale trusses are useful. The proportions are very important. And actually, when you're doing this, how do you proportion, say, the chord versus the vertical? How do you make one bigger than the other? I actually find that Lagrange multiplier is very, very helpful in determining the relative proportions of the beam that's the chord versus the beams, which are the web members. And actually, in that paper I showed you from 1992, I actually discussed this. And so I use Virendale trusses all the time, but when I can't get a diagonal.
Okay, thank you, Mr. Baker. Now this question is by Emerson Quilumbanquin Alvarez. Dice, thanks, professors, for your remarkable presentation. Please, in order to start our preparation and reinforce our knowledge, what essential bibliography will you recommend?
Oh, that's a tough question. If you can see my room, I have a couple hundred books behind me. And if I look behind you, you're in the library or something. You got a lot of books. Yes. Okay, what are the essentials? For tall buildings, I recommend reading Foster Kahn's papers.
Okay.
There's some good ideas which are still good ideas. We publish a lot. Everything we do new, we generally try to publish. Boy, it's tough. I'll have to struggle with that a little bit. To the extent you can read primary material, that's good. I've recently written a book or edited a book on
your book. Your book.
Yeah, where we took Maxwell's original papers and tried to translate it from English to English. It's from 19th century English to 21st century English. But the bibliography, that's a good question. I have to think about it. I don't have a good answer.
Thank you, Mr. Baker. Now, here another question by Juan Andrés Ospina. Dice, to what extent did the irregularities in height and plan influence the Burj Khalifa project? On the other hand, to what extent was the accidental torsion of the determining factor?
We designed the irregularities. In a tall building, wind is the dominant thing, and so we used to have a model here. Looks like my model walked away. Anyway, What we did is, if you have a building that's a uniform shape, I do have a model of the Sears Tower here. If it's a uniform shape and the wind goes around, it goes from side to side. And if you have a very uniform building, you'll get very big forces, and the building will start to rock from side to side. And one of the ways to address that is the shape of the building. And every building
for the wine.
For the wind. And so as you every building will have its natural frequency, and if the vortex shedding happens at the natural frequency, you get very big forces. And so what you want to do, but the rate of the vortices are related to the shape of the floors. And so by changing the shapes, by changing the shapes, the vortices happen at different frequency. And for me, the analogy is like a child on a swing. If you try to get a swing going, you kick and you go higher and higher. But the Burj Khalifa, instead of doing this, it has like 27 feet, and it never gets going. Okay, it has forces, but not very big forces. So that was the irregularity. Then on the structure, what we did is, this is conceptual also. We imagine it as if it was a giant extrusion, one structure, and then you trim it. You cut it out until you have the structure. So don't look at it as if you're adding things from the top down. Look at it as if you're going from the bottom up and you're removing things, which is very much the Sears Tower. You're going
Yes.
you're going from now. Do you have hot spots? Yes, because you'll have part of your building which is highly loaded next to a part that's very low loaded. So you have to move the loads, and so we did. In our link beams, we had to put some embedded steel shapes. We published a paper on that to get the load so spread out. But yeah, it's and so the shaping was actually a structural parameter. In fact, the very first building shape we designed when we won the competition did not work. Okay, our forces were too big, the motions were too big. And so we went back and we did a lot of changes in the shape, and the forces went way down, way down. It's a very, very quiet building from the point of view of wind.
Thank you, Mr. Baker. Now, this is a question by Rodrigo Gras Jimenez. This is thanks. What do you think about P delta effect in nonlinear analysis?
Well, P delta is real, okay. And so now. When I was a junior engineer, we had to estimate it. Now you can calculate. We always do P big delta, P little delta calculations on our buildings to get the second order effects. But we also look at the first order without, because that tells you how close you are to buckling. So we call that the if you take a representative deflection, okay, and you have a deflection with linear without P delta, without P little delta, you get first order deflection, and you got your second order deflection, and you take that ratio. That's a measure of the buckling load. Okay, we call that the amplification factor, and that's usually equal to 1/1 minus P over P critical. Mm-hmm. And so a lot of times, in order to keep your second order effects under control, you want to look at your first order deflections. And that tells you that's a very important design criteria, because that tells you how close you are to buckling and how much you are generating additional forces due to instability. So it's a very important parameter. And a lot of times you really want to limit it to like maybe 20%, second order to first order 20%, maybe 30%. But that not much more than that, okay, as a design parameters. And a lot of times, if you just look at how much the building moves under wind, under uniform loads, if that's on the order of 1 in 500, you're probably in a good place. That you can refine it from there. But that you got to look at second order effects, but it's also very important to look at first order effects.
Okay, thank you, Mr. Becker. We're going to the last three questions. Now, this question by Give me a second. Elmer Frey Torrico dice, nonlinear properties of materials are considered in the methods of theories that you present?
It's, how should I say that? Generally, everything I've shown is more linear theory. We're concerned about nonlinear, certainly for seismic, and for like creep and shrinkage, so long-term movements of the building. That's all nonlinear. But generally, wind loads are which I've talked about, so seismic is definitely nonlinear. Wind loads are generally linear because they're transient and not there very much. Do we look at nonlinear? Yeah, we definitely look at nonlinear. But in the design phase, it's usually not as dominant. It's important on the analysis and strength and make sure that you're safe. And certainly we look at nonlinear deflection of slabs and beams and stuff like that. That's over there. And we look at creep and shrinkage and all the time. Nonlinear, but and we also look at and we do look at buckling. Okay, first order to second order. I talked about the design of grid shells. Well, what I talked about was coming up with the geometry of equilibrium. You've got a structure that's pure axial. Well, you better check buckling.
Okay.
And be sure you don't have nonlinear snap through or something.
Okay, Mr. Beckett. This question is by Isaac Meta. Is it when you should the effects of internal force be neglected when applying Maxwell virtual world method? Isaac Briseño, perdón.
No, you're when you're doing the virtual work, it's really, I'm sure you've all had class in virtual work. Go back and look at it again. Okay, really think about it. So what you have is you got the forces in all the bars from a unit load case at the point that you want to look at deflection times the change in length, the internal work of the change in length of the bar due to the real load cases. And so, that's definitely internal work. Okay. So my equation I showed you was delta equals summation of NFL over EA. Well, that's the internal work. It's internal virtual work. And it's kind of virtual because it's two different load cases coming together. And it's totally bizarre that it works, but it's totally amazing. Because if I have a structure, it tells me, let's say I have a bridge and it's moving too much. I put a unit load on there. And when I design a new build, if you have a new building, you'll have 1 million deflections. Guess what? You don't care about 1 million deflections. You care about how much a bridge moves in the middle. You care how much a building moves near the top. And you put a unit load on there. It tells you how much every single member of your structure contributes to that motion in that direction. And if I put the unit load in a different direction, I'll get a different component, because you're not even measuring the total motion. You're measuring the motion in the direction of the unit load. And it's
Okay, thank
it's
you,
really
Mr.
It and Maxwell load path are my two favorite theorems for design.
Okay, thank you, Mr. Becker. Now the last question of the public is by Anna. What was the strategy for maintaining stability and structural integrity during and after the construction of the Burj Khalifa, and how were the design functionality and aesthetics successfully integrate into such an imposing building?
Well, I mean, my firm, Skidmore and Smith, we're architects and engineers. Okay, so I led the engineering team. Adrian Smith led the architecture team, and we talked like 10 times a day. I don't know, so it all came out together. And so the whole thing, and the system is naturally stable. I mean, we're designing a giant beam, and we designed the building for the final configuration. We also looked at the building during the construction sequence. We built the building in our computers as a stage going up. And so that lateral system, that I showed you, what we call the buttress core, that's a giant beam that works. It's a giant cantilever beam. The walls are either a flange or a web. They're either delivering shear or they do a little bit of both, actually. Just like in an I-beam, you have, the web takes a little bit of the compressive force too. And so, the stability was ensured. And the building is very, very stable, okay? And it's instrumented. It's got a lot of instruments. It's moving as we predicted. It's a very, 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 very stable structure that doesn't move very much at all.
Okay, thank you, Mr. Baker. I have two final questions.
Okay.
One technical and another is more inspirational. So, what is your opinion to use the virtual work in combined structural walls, like a steel tube frames and non-structural masonry? Could you be possible to analyze?
Could you? I don't see the written version. Could you say that again, please? The question.
Okay. What is your opinion to use the virtual work in combined structural walls, like a steel tube frames and non-structural masonry? Could be possible to analyze?
Very, very possible. Okay. But what's interesting about virtual work is it tells you the contribution of every member. The member could be a wall, could be a column. It could, it could be the column is steel and the wall's concrete. It could be a diagonal. It could be a beam with flexure, or it could be a pure axial member. And virtual work can deal with all that. And I showed how you can minimize for deflection. And you might notice in the calculations, every member can have a different modulus elasticity. Okay, and you can actually use Lagrange multiplier for minimizing embodied carbon. So what you do instead of volume, you take the volume times the embodied carbon per unit volume, not weight, but you take the volume of each element times a value, call it C, which is the embodied carbon per unit volume, and then you can minimize for embodied carbon, and you can have a structure that has flexural members and axial members that has concrete, steel, and timber, and you can optimize. So okay. It's a very, very powerful tool.
Okay, thank you, Mr. Baker. Finally, what advice will you give to young engineers and students who are beginning their careers to better prepare for the challenge and opportunities that this new technology era will bring? Okay,
first of all, while a student, take as many theoretical classes as you can. Okay. Now, I went to University of Missouri for 4 years. I got a degree. I didn't work for 4 years. And the thing I learned during my work process is that I didn't know anything. So when I went to graduate school, I took a lot. And then I took my master's, and I spent a whole nother year just taking classes in theory. And then I became a designer. Okay, so number one. All right, so get as much theory as you can while a student, because theory is hard to learn on the job. It's easy to learn, not easy, but it's easier to learn in school. Number two, do not take your first job for the money. Take your first job for where you're going to get the best experience.
Okay.
Your first job is very critical to your philosophy of design for the rest of your career. And so, it's very important to go where because in many ways, your first job is like graduate school. You get paid better. Okay. Mm-hmm. So, it's like graduate school with a good stipend. So that's number three is, as students, you're used to being poor. Okay. Poor. The ability to be poor is a great freedom. Okay. Yes. The minute you start buying a new car, you buy a house, guess what? You're no longer free. You can't change your mind and go back to school. You can't do something else. So try to stay. Make some money, put it in the bank, but don't change the way you live. Live like you're a poor student for as long until you're really sure that you're doing what you want to do.
Okay, so Mr. Baker. Those are three. Thank you. I agree with you. So, Mr. Baker, on behalf of the university, we would like to thank you for sharing your experience, knowledge, and vision with us. Your lecture has been truly inspiring and will certainly encourage us to keep learning and to face the challenge of engineering with commitment. Thank you very much.
Okay. Thank you for having me.
If for me, it's a great honor. It's a dream come true. Entonces, muchas gracias a los asistentes. Con esto finalizamos la primera conferencia. Entonces, los esperamos puntualmente en el otro link. Muchas gracias a todos.